Welcome to Meter Chalk Talks. My name is Leo Rivera. I'm a research scientist here at Meter Group. Today I'm going to talk with you about measuring water flow in streams or channels. One of the most common tools used for making this measurement are weirs, along with a water level sensor like our Hydros 21 level sensor. A weir works by acting as an obstruction in a channel, which will cause the water to back up, creating a ponded head behind the weir. That ponded head is measured with the level sensor and is a function of flow velocity, which allows us to calculate the flow rate through the weir. Weirs come in a variety of types, including V-notch and rectangular weirs. The shape of the weir will affect the overall sensitivity of the measurement. So, for example, if your goal is to measure low flows with a higher precision, then you might opt to use a V-notch weir like shown in the example here. If your goal is to measure higher flow rates, then you might opt for a rectangular weir. As we think about this measurement, one question that comes to mind is, what can our flow data tell us? So, I decided to install a V-notch weir with a 30-degree angle in a seasonal stream here in the Palouse. This stream is primarily fed by seasonal perched shallow groundwater and runoff from precipitation. The goal was to see if we could measure the diurnal pattern in stream flow due to plant water uptake and hyporheic exchange as the plant roots are interacting with the shallow groundwater. So let's look at the data from this experiment. The stream discharge is shown as the blue trace, measured using the Hydros 21. Evapotranspiration, or ET, which is shown as the green bars, and precipitation, which is shown as the blue bars, were measured from an Atmos 41 weather station. We are catching the seasonal stream at the very end of its season as flows are beginning to diminish. But luckily, we were able to measure a couple of good rainfall events, which resulted in both surface water runoff and increased flows from the shallow groundwater table. So as we dig deeper into the data, we see on June 13th, we had a more intense rainfall event, which resulted in runoff and a more rapid spike in our discharge measurement, which you can see here. On the 14th, however, we had more precipitation than the day before, but it was at a much lower intensity, which allowed the rain to infiltrate. Because of this, we don't see a large spike in our discharge measurement. Rather, we see a delayed increase in our discharge over the following days. Following that, we see our discharge begin to decrease as our ET demand continues to increase. You can see that here. Now, like I said before, our goal was to look at hyporheic exchange and see if our measurement was sensitive enough to measure this diurnal pattern. So let's look at June 18th through the 21st. On June 18th and 19th, we had fairly high ET rates, resulting in larger swings in our diurnal pattern of discharge. So you can see that here. You can see the higher evaporative demand, or higher ET, indicated by these green bars. And then as you look at the blue traces, you can see the larger swings in our stream discharge measurement. Now, on June 20th, our ET demand was much lower than the previous 2 days. This reduced ET demand results in a smaller swing in discharge. You can see that right here throughout the day. These data indicate that we are able to observe changes in the diurnal pattern of discharge due to the interaction of plants with the seasonal perched groundwater table. This means that we can use a V-notch weir to look at relatively small changes in discharge rates. So, if we were to take this information that we've learned from this experiment here, what this tells us is we can look at discharge information from a V-notch weir and also use it in applications such as measuring fluctuations in dry weather flow. So let's look at this example here where we're trying to look at dry weather flow fluctuations. And what we're trying to do is set thresholds. So here we have an example of 3 different thresholds, and primarily what we're interested in is when the discharge rate reaches the yellow and red thresholds. These thresholds can be used to detect anomalous flow from transient sources such as over-irrigation, broken underground pipes, or groundwater flow, which is entering our stormwater discharge system. And what this tells us is flow measurements from a weir have the sensitivity to detect the impacts from these influences on our stormwater discharge.